Good afternoon, everyone. My name is Michael Keogh, and I'm joined today by Rusty Wickel, and we're talking about reducing MTTR, or also known as mean time to resolve, and false escalations, and the event correlation system that we've built at LinkedIn. So following on from what Niall was just talking about earlier in here, raise your hand and keep it up if you've ever been woken because your service is unhealthy because of a downstream. All right, got a good over a third. What about, have you been woken if someone believes your service is responsible for breaking their service? All right, a few more hands. And put your hand up if you've spent hours trying to work out why your service is broken. All right, so we've got nearly everyone. All right, so me too. And for those who didn't raise their hands, I want your job. So today we're going to talk about how at LinkedIn we've tried to combat some of these problems. So just quickly looking at what we're going to cover. So we'll look at the problem statement that we're trying to address when building an event correlation system at LinkedIn, some of the architecture considerations, and then we'll talk about how we built the platform and then how that fits into our ecosystem of monitoring and alerting. And then we'll look at some of the key takeaways from the project that we've executed on. So we're a part of a team at LinkedIn called Production SRE. And the tenets of the team are to help restore stability during site outages, develop applications to improve mean time to detect and mean time to resolve, provide direction around guidelines for monitoring, and also build tools for efficient site issue detection, correlation, and troubleshooting. So you can see how an event correlation system fits into our team goals. So when it comes to the actual problem statement for building an event correlation system, we go and visualize this. As All right, so as our services get more complex, the reliability can go down. As our services get more complex, the learning curve for them becomes steeper, and especially in a very distributed microservices-oriented architecture like LinkedIn, the learning curve can get high quickly. And then as our services get more complex, you do risk your mean time to resolve on incidents being higher. And of course, mean time to resolve on incidents being higher is bad for customers and also ourselves as engineers. So when it came to sort of breaking this down a little bit further, so the three key things we get out of this is understanding services is hard, especially when you have a high velocity in development. High MTTR is bad. And then the other thing is false escalations is one thing that we really wanted to get rid of. And false escalations partly came out of a lack of understanding in services and some dependencies, and something that we felt that we could eliminate. So when it came to the project goals, two things we wanted to build. Firstly was a unified API, and then also a front end. So API provides hooks for other automation systems at LinkedIn to sort of go and query data and try and work out what happened at a particular time. Then also a web front end so we could visualize some of this. And then the tangible results is basically reduced MTTR and reduced false escalations. So we can let our SREs sleep during the night, or even if they are at work, not be interrupted as much. So when building this system, having all these goals is good, but we also had to scope, what can we solve and what can we not solve. So the applicable use cases we came up with were basically internal applications showing high latency or errors, 500s, etc. Non-applicable use cases were external monitoring systems, so like Catchpoint, Keynote, Pingdom, etc., showing latency or errors for LinkedIn.com. The reason for this is basically there are way too many dependencies between where the monitoring agent is and LinkedIn. And for us to try and consider all of these outside variables in an efficient way and keeping accuracy is actually really difficult. All right, so architecture considerations. So there are a couple of ways you can go about doing this. And as we'll go on through the talk, you'll see that it really depends on your own business and what sort of budget you have to do this. So firstly, there's real-time metrics analysis. So basically running metric correlation through stream processing systems. There's ad hoc metrics analysis, where you can sort of go and pull data and perform analysis on demand. And then there's alert correlation, where you're basically processing alerts from your monitoring system and trying to find causality. So let's run through all of these. So firstly, real-time metrics analysis. So the cool thing is it's fast. You're continuously analyzing your metrics. And in this case, metrics is time series data, just to be clear. And you can do advanced analytics in pretty much real time. The problem is it is resource intensive, so it does get expensive quickly. At LinkedIn, we're a fairly large infrastructure, so if we're going to try and stream process, all of the metrics that we emit every minute, it wouldn't be feasible. For smaller businesses, the resource ask may not be as bad. So ad hoc metrics analysis. So we have a trade-off here. We have a smaller resource footprint, but our analysis time is more slow. And there's a trade-off is how much do you scale back in resources and what the return is in terms of analysis time. Then alert correlation. So the pros here are is basically you can go and leverage existing alerts in your system. You don't have to go and do anything more. And you've got a strong signal-to-noise ratio, hopefully. If you have an alert firing for a system, that should mean the system is under duress of some sort, and so you've got that as a really good signal. The cons are your analysis is basically constrained to an alerting state, so it's a Boolean. Is it alerting or not? Which can be it takes away a little bit. So when we break it down, basically we see that alert correlation gives us a strong signal. Real-time analytics is expensive, but useful and fast. Ad hoc metrics is a little bit slower, but it is cheaper. So using this sort of basic analysis, we went and looked at building our platform. So before we started this project, there are already some other efforts within LinkedIn sort of happening. They weren't sort of formalized projects, but they were projects of interest and potential. And so we wanted to leverage these platforms that we already had started investing in into our system. So Rusty will talk a little bit later about the alert correlation system that we have. We also had an ad hoc metric correlation system using k-means analysis. The problem is with these systems is understanding how services depend on each other. So if you've got a database, several layers down in your infrastructure throwing errors, we need to be able to work out is the extra 500s that I'm seeing on my front end a cause of that or not. So understanding dependencies is super important. On the other end is when we were basically performing this analysis, we have two engines performing analysis all the time. We actually need to sort of collate that data and also decorate it a little bit and adding some extra context for the on-call engineer. The great thing about this system is, for those teams that do not have, on-call while they're sleeping, if they do get woken up at 3 a.m., we can provide instant information to those teams with some sort of context on what we think may be breaking their service. if they do choose to be woken. They can ignore it if we're pretty confident that something downstream is broken. So just to give everyone a little bit of context before we walk through some of these systems a little bit more, more deeply, this is what our system looks like. So on the right-hand side, we've got our call graph system. So we go and basically build a model of our topology and the dependencies between our services, put it in a graph database, and then we have an API front end which we can go and pull that data from, or users can go and make queries about their dependencies or who depends on them. Then on the left-hand side, we have our actual correlation engine. So we have APIs on the left, users on the right, coming into a front-end API. Then we have a system called Site Stabilizer, which basically acts as a proxy between our two correlation engines, Drill Down and Visualize. And what Site Stabilizer does is it basically works out, all right, who has the stronger recommendation, adds some data to that, and then feeds that back up to the front end. And of course, these correlation engines depend on the call graph to go and work out the dependencies. So if we go back to our original problem statement, basically, that as our systems get more complex, reliability goes down, the learning curve goes up, and the chances that our mean time to resolve goes up is pretty high. And so one of the things we did to sort of conquer the understanding of services is build the call graph. And this helps with our learning curve because we have scattered knowledge across the company of what services depend on what. As good a craftsmen as we try and be with our engineering, we can't 100% rely on documentation. And LinkedIn's velocity in development is actually really, really fast. Some services deploy 3 times a day. So dependencies may change. The amount that service A depends on service B may change daily. So it is important to understand our dependencies. So this is why we built the call graph. So we go and programmatically build a topology of dependencies between our services every day at LinkedIn. And so we provide an API interface and a user interface to this system so that engineers can go and have a look at what their system depends on in a very fast and easy way to see. And equally, if they can go and work out what services call them as well. And in this call graph, we also store information about call counts and latencies and error rates. So we can actually sort of work out roughly proportional distributions of how much does service A depend on service B, and how that works downstream. So how do we map a service? So there's sort of 2 parts to this. Firstly is service discovery. So at LinkedIn, we have a system called RESTly, which is our service discovery mechanism, which is based on Zookeeper. So we can go into the RESTly APIs and work out what services provide what APIs. And then on our services, we have very, very standardized metrics for our services. And using these metrics, we can go and work out what APIs our services are calling downstream. And using that data, we can go and build the call graph. So I'm going to hand it over to Rusty now to talk about how we use that call graph data in our correlation engine, Site Stabilizer, and in Visualize.
All right, my name's Rusty, and I'm a senior operations engineer. And let's see, what's next here? So now that we have a call graph, the next step is to be able to analyze the data. And the first tool that I'm going to talk about here is Site Stabilizer. Site Stabilizer, I can't see the screen. All right, so now that we have the call graph data, we want to be able to analyze it. And the usual method that we had in the operations area was to do this manually. So you guys probably have something similar to where you have a service A that's broken and you want to look for the downstreams. So you probably have a dashboard that shows all your dependencies. It may show your latencies, your errors, and so on. And from that, you're going to be able to find out the particular pattern on a particular downstream. And from there, you'll probably look up that downstream's dashboard, and so on and so on and so on, till you find the very root cause of that issue. How many people out there, by a show of hands, have similar type of dashboards where you look up your downstream dependencies or of some sort? Okay, well, it's a pretty common way to do that. So what we did with this is you would want to start analyzing these so that you could find that downstream. So several of the challenges involved are, one, when you're automating this process, is what are these thresholds going to be? So not all of our metrics necessarily had very defined thresholds, and we need these to be very dynamic in nature. Another challenge is what type of machine learning or statistical methods are we going to use in order to analyze these metrics algorithmically. So what the Site Stabilizer team landed on was using k-means. So k-means is an unsupervised machine learning algorithm, and it allows you to take a certain number of observations, in this case n observations, and to partition them into k number of clusters. So we focused primarily on 3 clusters so that we could either say it's below our threshold, it's either in its normal operating range, or it's above threshold. Now these observations can be then passed to k-means, and k-means can say, hey, I think it's in this particular cluster. And mostly we're just concerned with the observations that fall into cluster number 3, above our threshold, in order to detect latency and error deviations. So the other aspect is when we train it, we can take a lot of historical data and we can run it through this, and it can be trained and stored for later use. Okay, so just a quick overview of k-means in this respect. We have our time series here, and k-means is going to break it up, in this case, into 3 clusters, because we're saying we're passing to the algorithm that we want 3 clusters. So as I said before, cluster number 1 tells us metrics that would fall below our threshold. Cluster 2 is our normal operating area of good, and 3 is above our threshold. Each one of these has a centroid, or central area to the cluster, that is then used in the calculation of Site Stabilizer's predict score. And this predict score is basically calculated by calculating the distance above that centroid, and that is accumulated for the minutes that you are trying to calculate that score for. Now, in addition to the predict score, Site Stabilizer uses 2 other metrics. One is the trend score, and that is basically just simply that if the metric is trending upward, the score will be higher, and if the score is trending downward, then you're going to get a lower score. Because we're basically, in most cases, looking for something that is trending upward when these alerts go off. So it tends to favor that. We also leverage week-over-week data in the instance that the predict score and the trend score may not pick up on this particular deviation. Oftentimes, the week-over-week data will show that there is some kind of deviation going on. So the typical workflow looks like we use the k-means as well as the trend score and the week-over-week data to create a combined score for that particular metric. And then from that metric, we drill down through the downstreams, just like we did manually with the downstream dashboards, to get a final score. All right, so the second system is called Visualize, and that was developed by myself in the Operations Center. And it focuses primarily on the alert correlation aspect, leveraging the alert system and doing visualizations of that. So this tool started as a visualization project, and it was basically so that the operations people could get that bird's eye view of the entire network. They could really see that overview, and instead of looking through numerous dashboards and trying to figure out which particular downstreams were having issues, we could have one picture view, and you could pretty much see that subset of alerts that are actually having an issue. This proved to be very useful. We use it every day, and these issues can be picked up in real time very easily. So the next logical step was, well, hey, if you can detect it by human pretty easily, let's put an API on it so that we can also get this information programmatically by being triggered from other alerts. So the main key parts of this system are, one, it polls our alerting system, so it leverages that part of our system. Every minute it will pull in the alerts that are in air, and this proves to be very efficient in the sense that if I have alerts for every one of my downstreams, that I can get that 1% subset of all the alerts that are in air without necessarily having to have a question of saying which service, I have service A and what are my downstreams. Then you have to go look for all these downstreams. If you have that overarching view, you can get that information very efficiently. It also, every minute, then it will take that data from the alerts and it will correlate it with the downstreams by using the call graph that we talked about earlier. Then it also, on a daily basis, it will take that call graph data and it will update its stats for average call counts, latencies and errors, and also standard deviations. And it uses that also to feed back into the system and create updated thresholds as needed. All right, so there's a couple of assumptions that are used for creating the Visualize score that are different than the way we described it in Site Stabilizer. So the key three things are, one, the higher number of alerts that you have for a particular service, the more chance that it's broken. Also, the higher call count for those downstreams, the more valuable that particular downstream may be to that score. And also, the higher the change in latencies or errors, there's a greater chance that that's the problem. So these three metrics all put together form the basis of the score. And I'll show you here a visualization from an incident that happened that we saw in the Operations Center. And it illustrates these three aspects of the score. One, you can see that certain lines on here are larger than others. That represents the call count of that dependency between an upstream and a downstream. Then also you have the width, the thickness of the line, which represents, the width represents the call count. The color represents the deviation in that metric, whether it be latency or error increases and so on. So it goes from like a yellow color, which is your kind of your warning state, to a red color, which is your severe state of deviation. And then the third part is the number of alerts. And in this case, what you're looking for is the number of lines that are converging on a particular service. So that you can say, up there in the upper left, you can see 3 front ends that are going to a mid-tier. And so all 3 of those agree that that particular service is exhibiting a higher deviation. And then also, many other services then are going back towards this one at the very bottom, back-end data store. And that means that they're all pointing to that same service as well. So that gives you a sense of consensus among front ends and mid-tiers that particular back ends or data stores are having an issue. And this turns out to be pretty important as far as determining which services are having a problem, because some services may think that a downstream is not having a problem, but no other service is seeing this particular problem with that service. But when you have this consensus among many different services seeing the same problem, it really helps increase the confidence that that particular service is indeed having a problem. All right, so a couple other things about InVisualize is it saves this alert state from every minute into its data store so that you can replay an incident. This can be very helpful if you're an SRE coming into an incident, say, 15, 20 minutes after the issue, and you need to get up to speed. You need to be able to see kind of a replay of that last 10, 15 minutes or more, and be able to have some context about the situation. It also is very good for postmortems, so that when you're going through that postmortem, you'll be able to maybe get more information than you could if you're just looking at it on the spot. Go a little more in depth. It also ranks the services based on a score, and it's accessible through the API. Now this score is back to those three areas that I was talking about before: call count, the number of alerts, and the increase in deviation. And that score is normalized between 0 and 100. And this score is key in going into the recommendations engine, which puts together both the InVisualize score and the site stabilizer score together. And basically it collates these together to determine maybe which one has a higher confidence or where there's agreement between these two scores. So the recommendations engine sits on top of these two, as I said before, and it expects an input of the service, the colo that it's in, and the time duration, the start and end time. And it takes that, feeds it back to these two engines, and gets an answer and collates the information together. And what it returns is the responsible service, along with the confidence score for that, and the team that owns it, and also decorates it with other information such as scheduled changes, deployments, and A/B experiments. So now we can talk about how we integrate this into the alerting system so we can actually take action based upon an alert to then tell us what is the downstream problem. Okay, so we start off with receiving an alert from our alerting system. And this goes into our auto remediation system, or it triggers, we call it nurse plan, that is our auto remediation system. And it has the service name, the confidence required, and whether to escalate if that reaches that confidence. It then goes and it queries the recommendation engine, wants to know what's wrong with service A, and then yeah. Okay, so it says, I'm 91% confident that this is the problem, and it returns it, and it will either escalate to that downstream owner or the original service owner. Key takeaways here is, understand the correlation architecture that you need and understand your dependencies. And something very key to this is also having that feedback loop so that you can take this information and you can determine the system effectiveness and maybe how many engineers were saved from escalations. And we can use this to train the system for better results. Me and Michael are just a small part of this team, and here's the others. I'd like to have a call out for Reynold, Kishore, and Ranjith. They're not here. They're from the Bangalore team that developed Site Stabilizer for the most part. And that's it.